تسمعوني صح؟ Yes, they are working perfectly, I guess. Can you hear me? Okay. Good evening, everyone. My name is Dana Al-Kandari, and it is my pleasure to welcome you to the Kuwait Foundation for the Advancement of Sciences Radiative Cooling Workshop. This workshop is part of the Flagship Projects program in the Research Directorate at Hvac, and it is an output of an assigned project funded by Hvac to investigate radiative cooling of selective surfaces technology to cool building spaces in Kuwait. The purpose of this workshop is to provide engineers and students with the background required for implementing radiative cooling technology in Kuwait. And it is in collaboration with Kuwait University, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, and the Association of Energy Engineers Kuwait chapter. Our speakers for tonight are themselves the investigators that took part in the previously mentioned project. I would like to welcome our first speaker, Dr. Woody Chicron. Dr. Walid is a full professor in the Mechanical Engineering Department at Kuwait University. His research is focused on thermal solar energy, indoor air quality, cooling energy efficiency, alternative refrigerants, and residential air conditioning. He has authored and co-authored more than 75 journal articles, conference papers, and a book on thermal engineering. In this workshop, Dr. Walid will be explaining to us what radiative cooling is, and later on in the presentation, he'll demonstrate the application of radiative cooling in enhancing ventilation for better air quality. Our second speaker, Dr. Nasreen Ghaddar, is a professor of mechanical engineering and the director of Munib and Angela Masri Institute of Energy and Natural Resources at the American University of Beirut. Her research is focused on sustainable air conditioning with renewable energy integration. Tonight, Dr. Nasreen will be describing the mathematical modeling and the applications of radiative cooling combined with the M cycle. Our third speaker, Dr. Surur Al-Ataybi, is a full professor in the Mechanical Engineering Department at Kuwait University, and he is currently the chairman of the department since 2016. Dr. Surur will be discussing the applications and improving performance of conventional air conditioning systems. Our final speaker for tonight is Dr. Kamel Ghali. Dr. Kamel is a full professor in the Department of Mechanical Engineering at the American University of Beirut. His research is focused on heat and moisture transport in thermal systems, thermal comfort, renewable energy, air quality, personalized ventilation, carbon capture, and Hvac systems. Dr. Kamel will be explaining the radiative cooling effect on urban heat. By the end of the presentation, we will be holding a 20-minute Q&A session. So if you happen to have any questions, you're welcome to use the chat on your right, and our speakers will be more than happy to answer all of your questions. I would also like to inform you that there's a survey at the end of the workshop for you to kindly fill out. We very much value and appreciate your feedbacks. Now, without further ado, let's get started. Dr. Walid, you may take over now. The floor is yours.
Thank you so much, Dana, for this great introduction. I would like really to thank the attendees for their time to be with us this afternoon. I know it's kind of, early afternoon, late afternoon, but I want to thank you for being with us and to listen really to what we're going to be saying about these important topics for Kuwait and for the whole Gulf and for the whole world, as many fact. I want to thank Hvac really for their effort and for their support, financial support in funding this research projects. This research project was conducted over a period of 1 year, and it was completed, and the outcome will be presented in this workshop. I want to thank the speaker as well for their time and for involvement with us in this important topics. As we all know, we're looking for not in-kind technologies for cooling. We are looking really to conserve energy and to have less power needed for the cooling purposes. And this material, I think it was mentioned by Dana as well, this material really would help us to decrease the amount of the cooling load that's needed for the building and therefore decrease the energy consumption in Kuwait. I would like to speak about the outline of this topics. Basically, I would say what's radiative cooling, and kind of give some background about radiation for the students who will be with us to understand really the concept. And Dr. Ghaddar would mention how the system is modeled mathematically, and that would lead this mathematical model that would lead into different applications. We'll speak about the application of this material in different situations. And, Dr. Ghali would also mention the effect of this material in the urban heat when it's installed in a city, for example, and so on. And we'll have some questions at the end. Dr. Surur will mention how this material could be used in improving the COP of the air conditioning system. And Dr. Ghaddar will also mention the not-in-kind technology on the use of this material in something we call it indirect evaporative cooling. So I think we have different applications. We have a good concept, and let's go on together to understand more about this material. Radiative cooling, as we all know, the sun, radiate energy to us. It's great to have in the winter time. In the summertime, it would give us some load on the buildings, and we'll try to limit the effect of the sun radiations on buildings. And this radiation comes to us in a short wave, basically. And this carries lots of energy to us. It will heat up the buildings, the surfaces, and so on. And, when the surface gets heat up, it will have some conduction, some convection from one place to another one. So this energy will be dissipated throughout the building by different mode of heat transfer. Solar energy, the highest comes to us in a short wave. It comes to us as ultraviolet rays as well as visible lights, and they both carry energy. This energy, when reach Earth, it will starts to move around. We have also a little bit of energy coming to us as a long wave, but usually those energy are not of concern because they are at a lower rate. So most of the energy that reaches us are a shortwave radiation. Now, basically, we want this Earth, we want the surface that's going to be placed on the roof to reflect this energy coming from the sun. So this is one of the characteristics of the selected material, to reflect some of the energy that's the incoming energy coming to us on the roof of the building, for example. And, this shortwave radiation is absorbed by the Earth surface, and we want to reflect it as much as we can. And the long wave that the Earth cools itself, basically, is a long wave radiation, because the Earth usually at night it cools itself by radiating back some of the energy in a long wave wavelength, not short wave, long wave. And this long wave usually is blocked by the air and so on. But we have a window that we could really take advantage of, a window where the wavelength is between 8 to 13 micrometers. So this is the window where we're really going to be concentrating on for the Earth or for the surface to cool off itself. Radiative cooling basically is a process at which a body loses heat by thermal radiation. So we're looking at surface that loses heat instead of gaining heat. So number one, the surface has to block some of the energy coming from the sun, and as well as it radiates some energy from the surface back to the space. So this thermal radiation arises from random energy level transitions in matter, and we want to lose this energy to the space. And usually we take the space as being at 0 degree Kelvin. It's an excellent sink for us. So all the radiation will go to the space. And as I mentioned before, in the form of long wave radiation, and this window 8 to 13 is our target. So this kind of schematic, how the Earth receives heat from the sun, and how the Earth emit heat back at night, for example, in a long wave. So long wave radiation is the process where the surface loses heat to the space during at night, and hopefully will also, if you choose the right material, This will also take place during the day. Radiative cooling can achieve cooling without any extra energy. You are losing the heat from the building at no cost of energy. This mechanism has the potential to dissipate excess heat from the Earth to the universe. However, this long wave radiations, as I mentioned before, is blocked by the, not blocked, but at least delayed by the presence of the gases in the air, oxygen, nitrogen, and so on. So what we want is we have to make sure between the range of 8 to 13 micrometer, we have a window where the long wave could emitted from the surface to the space, and this is what we're going to be looking at. This is schematic, basically showing the emissivity and showing where we have a high emissivity between 8 to 13 long wave radiations. This is kind of energy balance. So the radiator could be the surface, for example. So the surface takes heat from the bottom, the building, for example, by conduction, for example, or by the water, could be water, for example. So the water loses heat, absorb the heat from the water, and this material also gets heat from direct heat from the sun and another diffuse heat from the clouds and so on. But as I mentioned before, the material also dissipate energy, emit energy in the form of long wave. This is the red kind of arrow. So energy balance, we want this energy balance to have basically the net energy will be losing energy instead of gaining energy. That's the whole purpose of the radiative material. Now, for this long wave to take place, for this surface to emit long wave radiation and this radiation to be effective, we want to have clear skies, because the cloud usually delay the process of emitting energy, and it will act as a blanket sort of to keep Earth warm. So clear sky will be a good thing for us to have when we apply radiative material. Another aspect is the low relativity, lower humidity, because the moisture in the air would also delay the process of emitting power. So any dry weather like Kuwait, for example, will be ideal for these applications. Low speed, we do not want the high speed to be on the material, because the energy would also be moved by convection from one place to another place. So again, low speed. So these are the three criteria. So the material would work perfectly, for example, in a clear sky, in low relative humidity, and in low wind speed. Of course, dust will kind of slow down the process as well. So we want to, basically try to clean the surface as much as we can. This is one of the pitfalls of this material when it's applied in Kuwait. So we have to couple it with always a cleaning process. So the material has to be cleaned all the time in order to work effectively. This is the Kuwait climate conditions. This is data we obtained for Kuwait. And you could see Kuwait is ideal because we have a low humidity. So when the temperature is high, the solid line is the humidity and the dashed line is the temperature. So when the temperature is high, you have a low humidity. So Kuwait basically is described to be hot and dry. And this dry weather kind of make this radiative cooling a prominent material to be used in Kuwait. So, we have the cooling season, which is June, July, August. Those are the months where we really have to high demand for cooling. The humidity is low, so radiative cooling could be very well potential to be used. And you could see later on from the application that we have very good effectiveness for the material on those in these months. The material that we select for the radiative cooling, of course, have to be available. We cannot create a material that's not available. Cheap, because we need to apply it in all the surfaces. It will perform good because certain thermodynamic thermal properties for the material has to take place in order for the material to perform well. And it has to be durable, as I said, because it's going to be outside. So it has to withstand high temperature, humidity, and different type of weather conditions. So it should have a high reflectance, because the short wave will be coming to this material. So this material have to have high reflectance, so it will reflect the short wave radiations. It should also have a high emittance on the long wave radiation. So the long wave has to have a high emittance, so the surface could emit heat in the long wave window. and also absorb heat from the bottom, because we want this material to be placed, for example, on the roof. So we want the material to absorb the heat coming from the building and then thrown it outside in a long wave radiation. Now, we have different material that are available. Okay, we haven't, it's under patent, most of them, so we haven't got the material to be tested physically, experimentally. That's why we had to go on numerical model really to see the effect of this material. But the material is very, very well described in the literature. So the first one is proposed by Bao from Colorado University. By the way, many universities have looked at this material. Purdue University have done a good research, Colorado, and it was initiated at Stanford University. So these three universities are the ones that really did a lot of work on this. And the cost is in the range of $7 per square meter, so it's not really an expensive material. The cooling power during the night is 150, because the long wave radiation is more effective in the night than during the day. So you could see the material will work best in the evening, not in the morning. And this is really where the breakthrough in this research that was done is to capture the cooling that takes place in the evening and use it in the morning during the peak time. So you could see later on in different applications, we have been using this material with some PCM, some storage, really to store really the cooling at night and then to use it in the morning during the peak time. So the whole idea is to shave the peak as well as decrease the energy consumption. Another research was done by Hang, another material, different type of material. He did not provide any cost estimates for that, but he had a cooling power of 180 at 300 Kelvin, and he reported as well, noon cooling in, of 100 watt per meter square. So all are very important thing. Is also another researcher. He described a certain material in the, he put 93 watt per meter square, and another one 127. So different materials are used on those surfaces, and the one we use in our work is that of Hvac in 2017. He described it, and I'm going to go over it again. I'm going to start from the bottom. On the bottom layer is aluminum sheet. The role of the aluminum, for example, to be placed on the tank, for example, or on the pipe, or on the roof. Okay, so to absorb the heat coming from the bottom. So the heat will be coming from the bottom, for example, from the building, go into that material, and then the intermediate one is silicon dioxide with a certain thickness, 20 millimeter. It will have a high emissivity because on the long wave, because we want this material to emit, like I mentioned before, this energy. And it goes to the top layer with the titanium dioxide. It should have a high reflectivity for the short wave. So the titanium will reflect the heat, the short wave heat, and the silicon dioxide will emit the long wave radiation. So by this combination, we tested this material by mathematical model to see its effectiveness. Dr. Ghaddar would speak about the mathematical model for this, and then we could get into the different applications. Dr. Ghaddar, the floor is yours.
Everyone, it's a pleasure for me to be in this workshop and explain some of the modeling work that we have done and the different applications of the use of radiative cooling as means for sustainable air conditioning or cooling for the climate of Kuwait. In mathematical modeling, I'll be presenting two components. One is actually going to be the radiative cooling hydronic panel, which Dr. Walid has explained how it works. And the second thing that I will also consider, the phase change material, because that's a component for thermal storage. As Dr. Chicron mentioned, there is significant cooling that takes place at night and less cooling that takes place in the day. So if I can use the cooling at night to also store it, to use it during the day, it's important to have that component model. So I'll be presenting the radiative cooling hydronic panel model and the phase change storage tank model. So for the radiative cooling hydronic model, you know, the cooling power is usually harvested by using a flow of water in tubes that carries that cool energy to take it to the application. The larger the area that you have, the more cooling power that you can harvest. Definitely, I cannot, if I'm gonna use this in an application, I have to remember that I only have 60 to 70% of roof area that can be used for harvesting of that material. So this was a constraint in all the modeling that we have used, models that we have used. The modeling is required so that I would be able to predict the temperature of the water coming out from the hydronic panel. And I would be able to predict the cooling surface temperature. Once I have that water outlet temperature, it's like a chilled water that I can use in the various processes of the cooling system. So we really, this is why it's important. The reason we choose water, because it's a high capacity fluid, it's a very, it's a passive material, and I can use it to run the system, the cooling system. So going to the next slide, I will explain how that model is done. Actually, what we are using, we're using a one-dimensional water flow in tubes that are little solar collector, you know. So the temperature of the water will be considered unidirectional, that moves from one segment to the next in one direction. I have the water flow in, and I want to predict in every segment how the water is going to change. I'm considering this problem, although it's one dimension, it's a transient, because the solar radiation, the heat quantities that are involved and the ambient conditions are also transient. And I have to make sure that the heat storage in the water term is including this effect. So I do an energy balance for a segment, for one of the segments here, I, and then doing the balance, I'm balancing the energy that is stored, that's the energy stored term, which is the density multiplied by the volume of that segment times the water heat capacity times the rate of change of water temperature in that segment. That must be equal to the net convected heat flow in the water pipe minus the heat lost through the RC panel, because the RC panel surface is cooled due to radiation exchange with the sky. An important component that I need to do here is to find out what is the net cooling power that is being lost from the water at the surface for a given segment R. So Q net is the difference between the outgoing radiation and the incoming radiation into the panel. It's really a balance of heat quantities. So it will be equal to Q radiation at any given time and for segment I minus Q atmospheric at any time minus Q coming incident from the sun, net Q from the sun, that is part of it might be absorbed, part of it is going to be reflected, and then minus QC. All these four balances of the quantities, this is a Q sun, you have Q radiation in green, a Q atmospheric, which has to do with the exchange with the sky, and Q convection with ambient air, or something, the Q conduction from the roof. So let me explain each term. Q radiation is the radiance emitted by the surface and is dependent on the surface temperature. That's a basic radiation equation. If I go to the second term, which is a Q atmospheric, it's the absorbed power due to the incident atmospheric thermal radiation as independent, and it is dependent of the ambient atmospheric temperature, T ambient. Q sun is the absorbed power due to incident radiation. So I have a Q solar incident, part of it is absorbed, and that's the only part that remains in the heat balance equation. And QC combines the lost and gained heat due to convection to the ambient air and upper side of the panel due to conduction through the roof. Moving from this, I would like to see what is that RC hydronic panel model going to give me. And I want to predict the water temperature. So I can discretize these equations. I start with boundary and initial conditions and solve the equations using a numerical model of implicit first order time integration scheme. The rest are algebraic terms. So what are the needed input and expected output of the model? I need the properties of RC panel, and those include emissivity, capacity, the thickness, reflectivity, and so on. I need the weather data because ambient conditions are crucial, and I need the water flow rate. And water flow rate is an input because you decide what is the flow rate in that hydronic panel, and you can try as many to fit your application. I use the hydronic panel model, and I get as output the temperature variation of water flow through the panel in the direction of the flow, and then the temperature of the radiative cooling panel surface. So I have the panel surface and water temperature. Now that I have these, I move to the phase change storage tank model, because that's going to be an element in my design to store the cold energy during that I get in the night and use it during the day. So daytime radiative cooling is usually used as a complementary source of cooling in a typical cooling application. It's complementary because usually the loads, especially in hot ambient, are much higher than what you can achieve with RC. More cooling is obtained during the night than during the day due to the presence of solar radiation. The use of thermal storage then emerges as undeniable necessity to store the cold produced by the RC panel during nighttime so that I can use it during the day. A phase change material, this is becoming a very common type of material. Usually it is made of some sort of paraffin and salts and so on, and you can always decide, depending on the mix of salts that you put, what should be the melting temperature. It's very cheap material. It has the ability to store thermal energy, but you can maintain it at constant temperature, which is the melting point of the phase change material, and it is commercially available. You can buy it off the shelf. At night, the PCM spheres solidify. They store the cold energy by the RC panel. During the day, this cold energy is released for cooling purposes. So part it absorbs, stores, releases. That is the process. And to model this is not very difficult because we're going to use a lump approach to model the phase change bubbles or spheres that we use in the storage tank. So what we are assuming is that we have a horizontal tank. Length is much larger than the height. It's filled with these spherical capsules of the phase change material, and the tank is fully insulated because I don't want to lose any heat to the outside. The tank is divided into different segments, just like when you are doing numerical integration. Each segment represents a single diameter of these spheres. And then you neglect the heat transfer in the sphere, and there is no spatial variation within the sphere. So one temperature represents that whole sphere. If it is melting, that will be the only thing you will be finding out as the cold water enters the tank at any stage, how much of that sphere has solidified, all right, or how much has been melted. So I get the cold water from the RC hydronic panel that comes from the RC hydronic panel. It enters the tank and starts solidifying. By early morning, you have the whole tank solidified at the melting point of that phase change material. The water temperature varies longitudinally in the flow direction. The tank has a length L, so you have cold water in, hot water out. So to go through the model, as I said, when PCM doesn't experience any phase change, it's a simple model that will experience an increase in temperature of the PCM material. So enthalpy change of PCM in each segment of the storage tank is given by the transient storage term, because I'm heating that material, or I'm cooling that material, and that must be equal to the temperature difference of the water across that segment multiplied by the heat transfer coefficient between the PCM sphere and the water multiplied by the surface area of that PCM. So the storage versus the convected heat between, the PCM and water. And you can do global conservation of energy inside each segment of the tank. So you have transient storage, net convective heat flow in the water. يعني انت عم تعمل للphase change عم تعمل للwater balance for that segment, and then the heat exchange between the water and spherical capsules. When I have during melting, the only parameter that changes is actually the melted fraction. How much of that phase change material has melted or solidified? And this turns out that the mass of PCM times the length, latent heat of a fusion of the PCM, that must be equal to the convected heat between the water and PCM temperature. So again, I go to the global model, where what is the input that I need to solve this model and what are the outputs? The input parameters, I need the properties of the phase change material. I need the water inlet temperature, the water flow rate. I use discretized form of the equation to put the model in numerical format as a code. And the output will be the temperature of the water in the tank at any segment and exiting from the tank. I have the temperature of the PCM spheres at any segment, and I have the melting fraction of the PCM when it is in melting or solidification phase. Remember, the melting phase is during daytime and solidification phase is during nighttime. So with these two models, I think we will move to the exciting part, which is the applications. How can we use this combination of RC with different cooling processes in a building, either office or residential? Thank you. I'm going to be off stage now to leave this to Dr. Sroor.
Okay. Good afternoon, everyone. I would like to take this opportunity first to thank Kefas for funding this project and for conducting this workshop. And also I would like to thank Professor Walid for the introduction of this project, and Professor Ghaddar for the mathematical model. And I would like to talk about the application of improving the performance of HVAC using this technology. Actually, one of the promising application of this technology is its utilization in HVAC system, and this is what we are going to see in the following slide. Okay. In this work, the hydronics radiative cooling panel is actually integrated with the PCM storage tank to assist the conventional HVAC unit in meeting the cooling load of an office space located in Kuwait during summer. As we all know, Kuwait climate is hot and dry during summer months, and which makes it very suitable for using this technology in HVAC. So before we go into the details, let's look at the mechanism of RC or radiative cooling in the system during the day and night briefly, and in the next slide we will talk in detail about it. During the night, the nocturnal radiative cooling power is used to regenerate or solidify, the phase change material, and this cooling power, which is saved inside the BCM material, is used later during the day to cool the fresh air. So this is happened during nighttime. During the day, the diurnal radiative cooling power is used to pre-cool the air supply to the condenser of the AC unit during the daytime to enhance its performance. So we are using daytime cooling and nighttime cooling in this system. Okay. Okay. How to incorporate this RC or radiative cooling with the HVA system to increase the COP? First, let's look at the cycle and explain the detail of the mechanism. What we have here, we have an office space, and we have a middle cycle. This middle cycle is coupled with two hydronic cycles. Okay. Actually, this cycle working in two modes. It's operate in two modes: one during the night and one during the day. Okay. During the night, we can see the red cycle, the red lines, okay, and the dashed line and the red arrows. This is during the night. The radiative panel cools the water, which is under the radiative panel, flow, which will later flow to the BCM, okay, tank to ensure the solidification of the material inside and to be used later. So between 1 and 2, we have the panels, okay, which is supposed to be mounted in the office space here, okay, and used at night to regenerate or solidify the BCM material, okay. The two other cycle, this is during night. The two other cycle will be used during the day, okay. So during the day, we have two other cycle. We can see the orange line, okay. So during the day, the diurnal cooling power of the radiative cooling panel is harvested for pre-cooling the air entering the air conditioning and heat heat exchanger 3 here. So the water leaving the radiative panel, okay, will move in this small cycle, okay, and exchange the heat with the air or the ambient air and heat exchanger 3 to be directed to the AC, to the condenser of the AC, to the AC unit. At the same time, during the day also, the BCM, which has been solidified during the night, now we can harvest the cooling, which have been saved in the BCM water tank during the day also by heat exchanger 5. So the water also will flow during the day in heat exchanger 5 and exchange heat with the fresh air, which will mix with the return air and also supply the air conditioning unit with this mixing air with the reduced temperature of the fresh air. So as we can see here, we are using the radiative cooling during the day in two times, or we are benefiting from it from two sides. One, the ambient air, and to reduce the ambient air going to the condenser, and one time to reduce the temperature of the fresh air going to the air conditioning system. Okay, this is just a schematic of an AC unit. We can see this is the air going to the condenser. If we could able to reduce the temperature going to the condenser, so to reduce the temperature of the condenser less than the ambient temperature. So in this case, if the temperature less the ambient temperature, we will be able to reduce the energy consumed in the compressor, because it will be directly reflected in the energy consumed or the work consumed by the compressor, which will reflect also in increasing the COP of the whole cycle. So just reducing the temperature of the condenser here, we will benefit from increasing the COP of the system. Okay. Move on. Okay, to assess the performance of the proposed system, a simplified model were developed, as we have seen previously with Professor Ghaddar, for each subsystem: the hydronic radiative system, the PCM storage tank model, and the space model. So we have three systems. These models were integrated to simulate the operation of the system and predict the reduction in energy consumption when the AC is assisted by the proposed hybrid system. The model already have been described previously in the previous slide. Okay, what we have seen here is the detail of the space and the assumption we are using. For the space here, the dimension of the space of the office space is 5 by 5 by 3 and located in Kuwait and occupied by maximum number of four people during working hours in summer between 8 and 6 p.m. The weather data of Kuwait was provided by the Meteorological Center for summer months, okay? And 15th of each month from June to September was considered as the design day of that month. And the office was exposed to the outside from south wall, and 60% also of which was double glazed, as you can see here. And each equipment is considered to have to generate 75 watt as an internal load. And also we assume that equipment and light is 16 watt per meter square. And the air conditioning system inlet temperature is set to be 20 degree centigrade. About the office envelope properties, we can see here about the ceiling, the external wall, and the internal wall, and the window. These are the properties of the layers, and their values are mentioned here in this table. What we can see here is the RC panel. This work adopted the design of Hvac, okay, in 2017, which consists of three layers, as you have seen previously: the emissive layer of silicon dioxide, and then the titanium on the top, and both are mounted in aluminum sheet. For the PCM properties, we are using the storage PCM storage tank, RT28HC. Paraffin was chosen as the thermal storage. Is also commercially available with the melting temperature about 28 degrees centigrade. Okay, sorry, 28 degrees centigrade melting temperature. And the total PCM material used is about 66 kilogram. Okay, and it was sized this 66 based on the month of July, which is the peak month. Okay, in our study. Okay. Okay. For the result, we have seen now that the system has been simulated. Okay, and we got some result out of this simulation after adding everything together. We can see in this table the improvement in the COP, okay, in the months of June, July, August, and September between the system with pre-cooling and without the pre-cooling. We can notice there is an improvement, a considerable improvement, in fact, in COP in all the months, okay, in the study. And it's vary between 18% to 34%, okay, which is considered to be high, and the maximum was 34, as you can see, improvement in the COP. The percentage of reduction of electrical consumption of the system will be also will be see it in the next slide. This is only for the COP. Okay. What we can see here in this chart, on the other hand, comparison between the cooled fresh air temperature, which is in the red line, and the ambient temperature, which is in the black line. Okay, during the day from 8 a.m. to around 6 p.m. We can see that the temperature of the fresh air after being cooled in this system, there is a drop compared, which is supposed to be this temperature, the fresh cool temperature, supposed to be equal to the ambient temperature if we don't have this system. But we can see there is a drop in temperature achieved with this technology. The drop in all the months between 12 to 15 degrees centigrade, okay, in all months have been achieved. Also, we can see that the fresh air temperature was around 28 at the beginning of each month. Okay, we can see it is around 28 at the beginning of the day of each month. Okay, this is the melting temperature of actually of the BCM. Okay, and it will increase slightly toward the end of the day. Okay, and it will reach around 30 degrees. Okay, this is due to the melting temperature, the melting process of the BCM sphere or BCM material during the day. It will be start melting because it is a transient process. So it will start melting from the beginning till it is finally melted, and all the cold energy being exploited at the end of the day. And we can notice this increase at the end of the day. Okay. In this figure or in this result, what we can see is the comparison of energy. Also, we have calculated the energy analysis, okay, to predict the saving of the proposed system and typical HVAC system. So what we have seen here is the months of June, July, and August, September, and the energy consumption in megawatt, okay, between the black column, which is the conventional, and the gray column, which with the radiative cooling system. We can see there is a clear reduction in energy consumption in all the months, okay, and the overall energy consumption reduction in all the months, this is overall, is around 37.74% during the 4 months. It is worth mentioning that the highest energy consumption reduction was found to be in July, which reached about 41.2 as a result of the proposed system to reduce the energy consumed by the HVAC system. Okay. Next. Okay. What we can see here is, as a conclusion, the hybrid passive cooling system assisting conventional AC system was investigated. The reduction in the system consumption needed to meet the cooling load of the office space located in Kuwait was assessed. The system we have under consideration is the hydronic radiative cooling panel plus a BCM storage tank, and then a mathematical model was developed to simulate the whole process of the system in the months of June, July, August, and September. Using the hybrid system helped us in reducing the energy consumption of the AC system by 37.74% with a considerable increase in the COP, or coefficient of performance. At the end, also the finding of this work has been submitted to a journal, Science and Technology for Built Environment. The title of the paper was Ventilation Increased Using Radiative Cooling and Phase Change Material at No Additional Energy Cost in High Ambient Temperature Country, and this work is still under review. Okay, so this ends the application of the HVAC, and I think the floor is yours, Professor Walid, for the next application.
Thank you so much, Dr. Sur. Great presentation. I guess now we need to discuss what else can we do with this system. We do have radiative cooling. We have hydronic system. We have water comes in, loses heat, and leaves colder than what it started. And this cooling process for the water vary throughout the day and throughout the months. Can we do more than only cooling the condensers? So here's we're going to be looking at application of this material of this radiative cooling in enhancing ventilation for better indoor air quality. Again, ventilations is so important, and especially now looking at the COVID-19 and the contaminations inside the houses, we could see that the ventilation will do a great job if it was properly done and it properly induced in the houses. So in the presence of ventilation, you could see the contaminations, for example, will be sucked back, diluted less, and it will be sucked back in the return and then thrown outside. So the supply, fresh air, for example, fresher, cleaner, it will dilute these contaminations out, and then it will return back and thrown outside. So when it is off, the particle will stay inside, and it will, settle on the floor sometimes, and then it will go from one person to another person. So this ventilation could do so much to us if it's properly designed. Of course, the role of the ventilation not only to take the viruses, but also the carbon dioxide and all those contaminations, particles at different sizes and so on, and the VOCs. Of course, we have many contaminants that we're relying a lot on the ventilation to clear out this contaminants from within the room. So for residential applications, especially in Kuwait, for example, we do not have enough ventilation in our houses. So that's what this application comes into the importance. Basically, we have a high temperature. We want to bring fresh air from outside to the house to clean all those contaminations out and to have a healthy environment and to keep people inside healthy. However, this ventilation needs to be cooled down. Temperature outside, for example, in the summertime is about 48 degrees C. If we bring it inside, we have to cool it down all the way to 24 degrees C. This is a huge cooling. And the ventilation load usually vary, of course, in Kuwait, depends on the weather, but it may reach 35% of the cooling load. So it's on the coil load. So this is really a big burden on the people. That's why people sometimes try to shy away from the ventilation, and they do not put enough inside the houses. So the question is, how do we meet the ventilation need? ASHRAE specify for us 15 CFM roughly. I'm talking about this roughly for per person, for people to stay healthy inside the house, inside their houses. So can we do something about this material and use it as to cool the fresh air coming inside to bring enough ventilation to the houses? So we're going to be looking at this applications, plus, of course, the application that Dr. Surur has mentioned to improve the COP by cooling the air going over the condenser. And he mentioned it very well and clearly that if air is cooler than going over the condenser, the COP will improve. So basically, and then this peak load is during the day where the temperature is very high. So the question, can we store this cooling in different phase change material PCMs and use it during the peak time and so on? So in the fresh air, and then bringing down the ventilation temperature, and in improving the COP. So this is really the application here in this paper. This is the house. This is the RC. So the radiative cooling. So water, go over or below the RC, loses heat to the RC, leaves the RC colder than what it enters. So if we put the heat exchanger, simple heat exchanger, and we have fresh air going over the heat exchanger, the air will be cooler, and then it will decrease the load on the air conditioning system. So that's basically an application, very simple applications. This simple heat exchanger, and if we look at the data, we look at the data part-time. Of course, the temperature varied during the day. We took, for example, June 15, July 15 and August 15, and we'll look at this hourly coil load for the 3 month. And we see that there is a reduction in the coil load, and this reduction varied during the day about 13%, and in the evening about 25%. So it does do a very good shaving the peak basically by 13%. That's very simple heat exchanger. We did not save any of the cooling at night or any of the PCMs. So if we need to improve this application, we could, of course, use storing the coldness that took place in the evening and use it during the day. This is where the PCM comes into the pictures. So here we're looking at PCM. Sorry, we're looking at the RC, hydronic. We have some water, some pipes. We have PCM. I'm going to put here PCM 1 and 2, tank 1 and tank 2. Tank 1 for the ventilation and tank 2 for the to cool the air going over the condenser. So keep in mind, tank 1, usually we want it to be cooler than tank 2 because we want to bring the ventilation all the way down to 24. But however, the air going over the condenser, we want to bring it down as much as possible during the peak time. Of course, and the air conditioning system. So here we have RC, hydronic, PCM2, 1 PCM2, and then the air conditioning system. Now, why we use 2 tanks? Because the water coming out of the RC is higher in the evening, okay? And then, we could decrease throughout the night, okay? So we could store this cooling and using during the peak time. And why we have 1 and 2, because we have the application is different. The ventilation, we need it to be at lower temperature than the air going over the condenser. So we're talking about 2 different applications. We're joining these 2 different applications. The one that mentioned by Dr. Surur, we could afford 28, 30 degrees C going over the condenser, and the ventilation bring it all the way down to 24 degrees C. So that's why we need 2 different PCMs. So tank 1, the PCM, will have a low melting temperature because we need to have it lower temperature. So we could design it with a different material, with the different melting temperatures, okay, low melting temperature than PCM2. And PCM2 is used only to improve the COP of the vapor compression cycle. So the panel, as mentioned before, it has been I mentioned it many, so far. So composed of silicon dioxide, titanium dioxide, and of course, aluminum to absorb the heat from the water. So this is how it is. So the PCM1 is basically, like I mentioned before, it has a lower temperature, melting temperature. We design it to be at 22 degrees C. And this is basically, we could cool down the temperature of the air going over the PCM, for example, to 22 degrees C and below 24 degrees C. And PCM2, we make it 28 because we could really, the air going over the condenser, we do not want it to be a very cold temperature. So, we have, this is more about the design of the PCM1, PCM2, which is very important to be designed properly, are in the paper. But basically, we need a mass of about 160 kilogram of this material, of these spheres, and the 200 for the PCM2. Depends on the sizes, depends on of course, on the temperature and the amount storing temperatures. So the application, I'm going to go over it very slowly here for this application. So this passive system, radiative cooling, combined with 2-phase change material, tank 1 and tank 2, was integrated in the air conditioning system. The idea is really to offset the increase in energy consumption related to the air conditioning during the high temperature. So fresh air intake, okay, in Kuwait, okay. So during the daytime, this is application for the daytime. During daytime, what we do here is we have fresh air. Fresh air is cooled by by a heat exchanger. We call it heat exchanger 1. And this is where the water coming from the panel. The water comes from the panel is cool. Cool. It goes over heat exchanger where the fresh air is cooled by this water. The water leaving heat exchanger 1 is circulated back, and it is again heat exchanger with the return, because we have the air in the room. We have supply and return. So the return from the room instead of throwing it outside, we pass it over the supply in a heat exchanger way to cool it down. It is at 24 degrees C. So we further cool the air after leaving heat exchanger 1 by the heat recovery system. We call it heat recovery system. The cool air then flows into a third heat exchanger for cooling via heat exchanger with the water exiting PCM1. So tank 1 is cooling the air further. So in 3 ways, the air is cooled in 3 different stages. 1 from the radiative cooling water, 2 from the heat recovery, 3 from the heat exchanger for PCM tank 1. The exhaust water is circulated back to tank 1 in a closed loop where it loses heat to the PCM. So PCM takes the heat from the air and then it goes into mixed with the fresh air, basically with the circulated air, and goes inside the room. So during the day, the air is basically decrease its temperature at 3 different stages. The first stage over the water from the radiative cooling. The second stage from a heat exchanger with the return air from the room, and the third stage from the water over the PCM tank 1. So tank 1 is used for the ventilation. Okay, so the exhaust air enters the mixing unit where it's mixed with the return air for further cooling in the air conditioning system to meet the space load. As for the cold tank, tank 2, it is used to pre-cool the air entering the condenser of the air conditioning system to enhance its COP at peak time. So this is really where the application is. So when the outdoor temperature is higher than the PCM2, the PCM2 would cool the air and the air will go over the condenser. So here we have 2 different applications, as I mentioned before, one for the ventilation and one for the COP. During the nighttime, we have 2 different evenings we're going to be looking at. We have to look at the early night and late night. At the early night, which is this, the one to the left, okay, early night operation. During early hours of the night, the early night operation is on when the temperature of the water exiting the RC is higher than the melting temperature of PC tank 1. So when it is higher than tank 1, that means it needs to be further cooled down. During this period, the cooling power of the RC is used to solidify tank 2. So now tank 2 starts to be solidified. We're storing some of the cooling in tank 2, okay? And tank 1 is used to cool the ventilation going to the room. So at the same time, the fresh air is being cooled by heat recovery process by a heat exchanger 1 with the exhaust, and then it's further going over the water for PCM tank 1, and it goes into the room. So the ventilation takes place by 2 things, 1 from the return, the heat recovery, and 2 by PCM1, and the RC is used to solidify tank 2 to store this cooling for inside tank 2. And then for later, which is the late night, for later at night, we have more cooling from the RC. This is when we start solidifying tank 1, okay? So this cooling power is harvested in solidifying tank 1. Tank 2 now would be completely solidified, so it's already getting its cooling capacity. So all the cooling takes place, goes to tank 1 for storing it for the next day. So the fresh air now is cooled by the heat recovery, the ventilation by the heat recovery, and enter the heat exchanger where it's further cooled by tank 1. So we have now, you're using the cooling that's from the RC 1 for tank 1 to further cool the ventilation and then to solidify tank 2. So now the application is we have during the day, early night, and late night. So this model was done as mentioned by Dr. Ghaddar. So the panel, we have 2 tanks, 1 and 2 for solidifications. It depends on what time, what hour, what month, and temperatures as well. So the input for the model basically is geometry of the house. We took the house villa type. physical makeup of the walls, floor, U values, internal gain, operations, all this stuff for the house. Transys was done to give us how much cooling load is needed. We have also the RC panel, and we have also the PCM, and then we run the model to get some results. This is kind of the villa type. We have about 500 meters square. The area needs about 70% of that area for the RC to do this job. Okay, and these are the input parameters, and this is where the saving is. This is where the saving is. So what we have is the fresh air average ventilation saving. So this is how much, like I said, 15 CFM is what's needed by ASHRAE. What does the system gives us? How much fresh air can the system gives us if we use it for ventilation? Per person, the system could provide a lot more than what 15 CFM, what ASHRAE is calling for, okay? So ASHRAE calls on 15 CFM, however, the system gives a lot more. So tank 1 was integrated with the PC. So this figure presents the fresh air flow rate per person supplied to the space, which exceeds the minimum requirement of ASHRAE's 15 CFM or 7.5 liter per second per person. Okay, summer months was maintained constant throughout the day, and the entire ventilation load was met by the proposed passive system. So we could meet what ASHRAE said and a lot more than that. And this, for example, depends, of course, on the month. In April, we could get 5 times more than what ASHRAE proposed. And in month of July, we could probably give about 3 times more or two times more. Okay, so we could really get a lot more ventilation more than what ASHRAE proposed if we keep the temperature the same. Okay, so this was predictable due to the relative low outdoor temperature during this month. I'm talking about the month of April. Okay. Now, on the saving, we have the fresh air. If I look at this one here, this is how much ventilation saving. The average ventilation saving of the proposed system with respect to the conventional AC system with heat recovery for the same fresh air intake is presented in this figure in here. In order to get the same indoor air quality, relying only on the conventional AC system, an average ventilation load is needed about 0.95. However, the system gives us a lot more than that. So we could have a maximum saving of about 4.1 kilowatt, okay, during the month of April. And in July, we have enough ventilation. So we could look here at the average. We have about 2 kilowatt, an average over all these months saving from the ventilation alone in this system. So now we're trying to quantify how much saving there is in both applications. In application 2, which is the PCM tank 2 on the COP for the system, for the air conditioning system. So where tank 1, tank 2 was used for the cooling, we could get, depends on during the peak hours where it's needed, we could get 5%, for example, in October, 12 because the temperature of October is lower. We could get the most in July because the temperature in July we could decrease it to 28 degrees C. So these are the saving from the COP. If we combine both together to give us how much percentage in energy over the cooling season, okay, April to October, we could see how much saving we could get from both applications, from the ventilation coupled with the air conditioning system. We could see that we have, on the average, 22% could be saved from the cooling load, from the energy that's needed for the air conditioning system if we use the system that was just described. So, in conclusion, we had this paper. It was submitted to ASHRAE journal. It's under review right now. We are using RC panel coupled with 2 different tanks, and the application we have varied between early night and late night. So tank 1 was used for ventilation. Tank 2 was used for to improve the COP of the air conditioning system. We run it together, and we got a saving of 22% with respect to if we couple both applications together as an average 22%, which is a great percentage for this type of applications. This is passive cooling. Next, we're going to look into the application where we could use this RC as a cooling process in indirect evaporative cooling. Dr. Ghaddar, the floor is yours now.
Thank you, Dr. Chicron, for the presentation of the second application. And we're going to move to something more complex, because in all our work, we were actually trying to find, is there a passive way by which I can have the place or the space air conditioned without having to use mechanical ventilation, even in a challenging climate, hot climate, such as the climate of Kuwait. The catch here is that indirect evaporative cooling can be used because you have a dry climate and a low dew point. And this is why the combination of the radiative cooling panel and the M cycle is going to work. Let's see how that has been done. And it was the first study in which this combination was done. We have significant nocturnal cooling power during the night, because there's a lot of sky radiation, there's no solar power. And there's a small cooling power during the day, right? RC on its own cannot deliver all the cooling load of the building. So RC needs another system that can support it so that I can have a sustainable cooling system. And what we chose was really the M cycle. Some of you may wonder, what is this M cycle? It's basically an indirect evaporative cooler. It's a device or equipment that is commercially available. You can buy this from US, from China, from Europe. It is an available device where, if I go to a psychometric chart, I sensibly cool the air to almost its dew point, instead of cooling the air to the wet bulb temperature. So I end up with much lower temperature than the wet bulb temperature I normally get when I have direct evaporative cooling. So what happens in the indirect, in the M cycle, you have two streams going opposite in two different channels. One channel has wet water film and the other channel is dry. So the ambient air goes in the dry channel, and then another stream of air goes in the wet channel. While the water is evaporating, it's cooling it's cooling the air, and the air in the dry channel is sensibly being cooled. It could, with a proper design, it could reach the dew point. And that's why we're going to combine it with the RC panel. However, the use of M cycle in air conditioning is based on water consumption. And that was the challenge for us. Can you really sell this product if you tell people for each kilowatt hour you are going to use between 2 and 5 liters of water? That's actually a lot of water. So the combination was nice by introducing a water reclamation technique. And what we have used, we actually used a well-known method for extracting water from moist air. This is called the air or atmospheric water harvesting, and it's based on batch bed in which I have silica gel. This is a salt that absorbs water, and until it gets saturated, in order to dry it, you need solar energy to to take that water out from that batch. So that's why I run it in a batch system, as I will explain later. So now I have a combination of the indirect evaporative cooler, which is the M cycle, that uses the pre-cooled air from the RC panel And then I have the humid working air goes to an adsorption or water harvesting system. It absorbs the air, it takes it back, I collect, and then in that batch system, I heat the adsorbed, the silica gel that is saturated, and I get the water out, I condense it and get it back in the tank. So I have a closed loop in which I don't lose water in that system. I don't need additional water. So now the application now of that full system, I can run the RC panel alone because there are certain times of the year where you have moderate weather, spring weather, and the radiative cooling will be sufficient to cover the required cooling load of the building. There are times where you will need to run the radiative cooling and the dew process indirect evaporative cooler or the M-cycle unit. We call it the dew process apparatus because this is how it is sold in the market. The circuit for this, the ambient, this is, I hope that the slides are clear for the numbers, but if you look at the figure in the left, it has the proposed hybrid cooling system operation where fresh air enters via an air-to-air exchanger at point 1 with part of the return air from the space, so, which is at lower temperature from ambient air. اللي هو عادة ambient air is larger than 45 degrees centigrade. The cooled air enters air-water heat exchanger because the cold water produced from the RC panel exchanges it and cools that air further. The exiting water from water heat exchanger goes back to the RC panel and you continue the loop. At loop 4. The cooled air exiting the water heat exchanger at 5 is supplied to the cross-flow dew process indirect evaporative cooler system to be cooled to the correct flow rate and to the correct temperature that you needed for the supply. That product air could be mixed with the return air based on the fresh air requirement of the system. As I said, the water harvesting system has a batch system formed of several sorbent beds. You have a daily cyclic sorption, desorption of the airstream that comes from the dew process dew point indirect evaporative cooler, and the collected water vapor is condensed and stored in a tank for future use. When the RC system is able to meet the cooling load alone, you can see it, its operation is very simple on the right side of the right side figure. The RC panel, as we selected the panel that I think that Woody Chicron has presented in the beginning of the workshop, and we applied the models of this panel on this panel. So just to save time, I will not repeat what its components are. So how we are going to apply this? The M cycle has 2 working streams, the product air and the working air. The product air is sensibly cooled in the dry channels, and the working air is sensibly pre-cooled in the dry channels while being gradually diverted from the dry working channels to the wet channels. So these are done through the cross flow holes, always to bring it down closer to the dew point. Based on the intake air conditions, water temperature and flow rate, يعني أنا عندي inlet conditions of the air coming in. And I have the water temperature coming from the hydronic panel with its flow rate. I apply the model and I'm able to get the temperature and humidity of the product air exiting dry channels that I want to use it in my air conditioning system and for conditioning the space. In working air leaving in wet channels, I have the conditions of this because I need to use it in the water harvesting system, and it will allow me also to find out what is the water consumption of that system. For the application of the RC panel with the M cycle, for the water harvesting system, as I mentioned, usually they are suitable because the most common type adsorbent used is silica gel type A. It's very cheap. and it has low regeneration energy, which means I can depend on solar energy to regenerate the water vapor and then condense it to water to get it back to the tank. Regeneration temperature is between 50 and 90 degrees centigrade, which is a low-grade energy. So this is the low-grade energy source can drive this operation, and the thermal energy needed for desorption is actually 2.7 to the power 3 times 10 to the power 3 kilojoule per kilogram of silica gel. So each bed undergoes several cycles to be able to reclaim the water that is needed for the cycle, for the M cycle. Now we're going to go to the same application that Dr. Chicron presented for the 2 typical story residential house in Kuwait. We took its properties. We actually calculated its load based on Transys. This is a well-known simulator for building energy analysis and so on. And the model requires having to input the geometry, the physical makeup, and so on to be able to find out what is the peak load that has been reached and what is the distributed hourly load for the whole year. The peak load was found to be ranging between 17 and 38 during the month of July. 38 at peak hour, and it could be at night 17. We used the thermal details of all layers that depend on the Kuwaiti building code, construction code. So the application here, I have 3 models. One, it's a space model, Transys, which is the commercial software. I need the geometry, I need the data, weather data of Kuwait, the internal heat gains, the schedules, and so on. And the output from this is the space cooling load hourly and peak. Then the RC panel, the radiative panel submodel will solve the differential equation to تعطيني water temperature flowing out of the RC panel. So I get the temperature of water out. I need all the properties of weather data, water flow rate, and properties of RC. For the M cycle, I need the properties of that unit. It's the geometry, the sizes of the dry and wet channel, and so on. And then I use the model and I predict the temperature of air supplied to the residence. Consequently, the obtained cooling load, min the Transys, I calculate that, and all what I want to make sure the output of air supplied to the space matches what is needed if I replace the conventional system. And of course, I need to do a lot of simulations to size the M cycle and the water harvesting system. So what we got, here are the results. What I'm showing here is the operation schedule of the RC system alone and when it's operating with the M cycle. So whenever you have a dash, it means I'm only operating the RC panel alone. So during the month of March, I don't need the M cycle. If I go to April, during the day, the number of hours in which I will need both systems is going to increase. So I operate the M cycle and the RC panel together almost all day hours and 2 hours in the evening. In May, again, I have certain hours of the day in which both systems need to operate, while at night I only need most of the night just the RC panel. In June, I cannot do without operating it all day for both systems, all right? In August, the same. As I get to milder months, dependence on M cycle is less and less. As a reflection of this, the results that we got, the M cycle system was not needed to operate during the month of March. That is the first finding. The system was shut down during March between 11 p.m. and 9 a.m. That's a lot of saving in terms of hours. In April, from 1 a.m. to 8 a.m., I don't run the system. During May, I have the combination, as I mentioned. And then June, July, and August, both systems have to be operating even at nighttime. so that I can get the cooling, and I can make also use of the dew point apparatus that will cool the air close to the dew point. What matters to me now is the energy consumption. And a significant reduction in electrical energy consumption was achieved because 53% of electric power was reduced when I compare it to the conventional AC system. You ask me, where did this electrical power coming from for the hybrid RCM cycle? It's really the redundant power that comes from pumps and fans, because you have all these fans that are driving the air in the duct, and the water cycle, you need a pump to have the water conversion. But I'm able to have a lot of savings when I use this system and without wasting water, because I use cycle, a closed cycle. So in conclusion, the performance of hydronic RC integrated with the M cycle and water harvesting system from the atmosphere in the hot, dry climate of Kuwait has been evaluated, and it has been evaluated for all the months in which air conditioning might be needed. And we were able to save 53% of electrical energy using this system. Future work, of course, can address the performance of that system. We can have an optimized operation with improved characteristics of RC panel, and maybe we can do a life cycle cost so that people know that if they invest in this, it's gonna work. Remember that I have a system that's a little bit complex and bulky. Thank you. And I'm gonna leave the floor to my colleague, Dr. Ghali, who has been with us also on all of this work, to take the stage.
I am on stage there. Okay. Thank you, Ms. Good afternoon, everybody. It seems that I am the last speaker. However, closing speakers are the most remembered because they speak last. So I welcome everybody, and let me start talking about the radiative cooling effect on urban island heat. Besides providing effective cooling power, the cool surface of the radiative panel will cool the air which is close to the surface, lowering its temperature and mitigating the urban island heat effect. Yani, as we have learned from Dr. Walid and from Dr. Surur and from Dr. Radar, the radiative panel relies on lowering its temperature by exchanging heat with the cool sky. So we will end up with a cool surface. This cool surface will not only cool the circulating water or circulating air, it can also lower the temperature of the air which is close to this surface. And by lowering the microclimate temperature of the air closing to this panel, we will be mitigating the urban island heat effect. And this is really mainly due to the physical radiation property of the panel, which is being highly reflective in the shortwave radiation with the high spectral emissivity in the atmospheric window. Let us look at the second slide. Okay, so the radiative panel are characterized by being highly reflective in the shortwave radiation, and they have high spectral emissivity in the atmospheric window, which is between 8 and 13. Now, to assess the atmospheric cooling effect of the panel, we used a very simple approach. We took two surfaces, one surface which is concrete, which is characterized by a reflectivity of the 0.3, a lower reflectivity, and in the shortwave radiation, and the radiative cooling panel, which is characterized by a higher reflectivity, 0.9. So we want to look at the temperature difference between the near surface temperature, near air temperature close to the surface, and the ambient air. So we are looking at what will be the difference between the microclimate temperature of the air close to the surface and the ambient air in both cases of having a concrete roof or the radiative cooling panel. Okay, so to quantify this amount of temperature difference between the microclimate temperature close to the surface and the ambient air, we followed the relation that was developed by Benny. Okay, and the relation that was developed by Benny, it depends on the radiation net effect, which is a balance between the short wave radiation absorbed and the long wave radiation. So to get the temperature, TO is the temperature of the microclimate temperature close to the surface, and the temperature of the ambient air away from the surface. Okay, so we are looking at this temperature difference. Okay, and to get this temperature difference, I need to get the RNet, which is, as I said, a balance between the short wave radiation and the long wave radiation, which can be obtained by the mathematical model that was explained by Dr. Ghaddar. Okay, and using this relation for both the concrete surface and the radiative panel. Okay, so we did this. Okay, and we did the simulation for the different months. Okay, from March to October, and what we noticed that for the concrete surface, okay, the temperature difference, that the microclimate temperature close to the surface is higher than the ambient air temperature away from the surface. Okay, and it peaks during noontime. Okay, during this sunshine hours. Okay, whereas the radiative panel, it's all temperature difference is negative. It's always less. The temperature difference of the microclimate temperature of the air close to the surface is always less than the ambient air temperature. And one thing that we noticed that that the temperature difference between the microclimate temperature and the ambient for the concrete, it can reach about 2 degrees. This means that the temperature close to the surface is higher by 2 degrees than the ambient air, whereas the temperature difference for the radiative panel, it can vary between -0.65 to -0.2, and it is effective for all months from March through October. We can observe this cooling effect of the microclimate temperature. So having said that, this is, as I said, a very simple procedure just to look at what added benefit we can get from this radiative panel. Okay, we can get, as was explained by my colleagues, the cooling power. Okay, but what about the urban island heat effect? So this simple exercise shows us that the temperature close to the surface will be lower than the ambient air. And this is very promising. And this really gives us an incentive to investigate the effect of deploying the RC panels on a large scale in the city of Kuwait, and to use a more advanced software like MVMet and other software, to look at the impact of using these radiative panels on the urban island heat effect. So in short, the simple exercise that we have done by comparing the effect on the temperature difference between the microclimate temperature and the ambient air for both surfaces of concrete and the radiative panel, shows us that we can lower the temperature of the microclimate air close to the surface. And as I said, we can in the future do more simulations on a large scale for the city of Kuwait to see what will be the effect on the urban island heat effect using more sophisticated software such as MVMet. This is the end of my talk. Thank you. I am done.
very much, Professor, in this informative and interesting presentation. We can now move on to the Q&A session. We have a few questions. Second. Okay, so we have a question by Dr. Isam. He says, the question is for Dr. Walid. He says, what challenges do you foresee to apply RC for ventilation to government buildings? Dr. Walid, you're on mute.
Yes, I see. Thank you, Dr. Isam, for this question. I think the challenging will be to have the material ready because, as you may know, the material is not commercialized yet. But once it is commercialized, I think with a little bit of effort, we could implement it. We have to make sure, of course, it's maintained properly throughout the lifetime. I think the material is cheap. It's proven to be safe and then cost effective. So I think all what we need is to get the material in hand so we could apply it. I think the space, we have to make sure that there's enough space on the roof for the material to be applied.
Thank you very much, Dr. Walid. We have another question by Yusuf. Thank you, Yusuf, for your question. Yusuf is asking, what would the overall energy efficiency ratio of this combined HVAC system be?
I think this is a good question. I haven't calculated the overall, all the energy input and the cooling that takes place, but this is very important. I mean, the saving is there, but to give you a number, it will, I cannot calculate it, but it's very important to do that.
Yes.
I think saving of Dr. Sur, I think you mentioned something about COP improvement. Yeah.
We have mentioned the saving in COP and the overall saving throughout the months, the 4 months, but we haven't calculated the exact energy EAR of the system in the whole months.
Okay.
But it can be easily converted. But I think the combination, all the system with the ventilation, with the improvement in COP, this would be very good exercise to do that.
Yes.
For lead and otherwise, yeah.
Thank you very much for your answers. We have another question for Dr. Nisreen by Magdi. Thank you, Magdi, for your question. He's asking, in the case of PCM, how do you get rid of the heat released when the spheres melt?
You have a continuing water flow. So the water itself, it leaves the PCM during the period where it's releasing, melting. Water will come at warmer temperature, but then it will be recirculated to the RC panel. So it's going to lose the heat and get cooled. Now, this is a closed cycle. And the way we have designed, there is a sizing approach. Somebody has asked that question of the phase change material storage tank. So what we do, we match the tank to our requirements, because you don't want, half the tank with melted, over melted PCM, and you don't want to have solidification while the water is much cooler than the melting temperature of the tank. So we do many simulations until we do the matching at peak load. If things are off, I get cooler water, it's fine. But at least at peak load, I am getting the water exiting at the melting temperature of the that we have selected in the application. This is how it works.
Nasreen, I believe we have another question by Magdi as well for you. He's asking, have you considered using a computer simulation tool such as a TRN SYS to model the RC panel?
sorry, what is the question?
Have you considered using a computer simulation tool such as
we use the we really have to validate whatever we are doing. We use the trances to get the cooling load of the villa, but we did not integrate the RC panel into trances. It requires some programming. We have this, but it was not on our horizon since we developed our own model and we wanted to do the sizing, but it's doable.
We also have a question by Muhammad. Muhammad is asking, how do you consider the area between PCM and the tubes?
I think the question meant the area between the gap between the radiative cooling and the.
And you mean
tubes.
the surface area of the cooling and the PCM tank? It depends. If I have large surface area that I can use for the RC hydronic panel, then I have high water flow rate, which will allow me to enlarge the size of the horizontal PCM tank. The PCM tank, it's all bubbles or spheres of PCM. We have done a lot of testing in phase change material, and we have these spheres. So you just pass the water between them, and the more flow rate you have, the larger your storage tank can be. So this is why the two are connected. And you just have to do iterations and to do the matching and the sizing. And then you can model the operation.
Thank you very much, Dr. Nasreen. We also have a question by Jalal. The question is it applicable for 100% fresh air cooling systems?
And fresh air is there, and then we could have saving as we have demonstrated. Can you guys turn off the mic?
Dr. Nasreen?
Yes, we can. The only thing is we do not recommend, ASHRAE does not recommend 100% fresh air. It will be waste of energy. ASHRAE has a certain code to say how much fresh air you need. What we need is only 15 CFM of fresh air to be embedded in the ventilation. But 100%, yes, we can, but it's going to be on the cost of other things. I mean, this is how much saving we could get from the RC. This saving, this cooling, we could put it in ventilation. You could put it in 100% fresh air. You could put it in cooling the condenser, in whatever you want. So this is kind of optimized system that we have. Yes, we can, but depends on the application. In the hospital, yes, you need 100% fresh air. Otherwise, you will not need 100% fresh air.
Thank you very much, Dr. Walid, for your answer. And I guess we don't have any questions, right? I guess we're done with the questions.
And if anyone wants to send questions to us separately by email,
hello?
So we do have some documents. If anybody's interested, you could download some of the documents, some of the resources. We have 4 different resources you could download if you want to. That will give you more information about the project and about the RC and its applications.
Okay, I think Dana, she went offline.
Sorry, there was something wrong with the connection. I guess we have completed the Q&A session for now. So Ladies and gentlemen, we have reached the end of the workshop for tonight. I would like to thank our speakers again for their time and effort spent on this study and the valuable information they've enlightened us with tonight. I would also like to thank our audience for joining and interacting with us. We really appreciate it, and we hope to see you again, inshallah, in future events. I would also like to take the opportunity to thank my colleagues backstage for their effort and support. Our program manager of the flagship projects program, Engineer Dina Naqib, our senior program officer of the flagship projects program, Engineer Anwar bin Amr, our IT specialist, Engineer Shabit Tuhami, and our communications specialist, Mrs. Sarah Al-Hilal and Mr. Mohammed Borisli. I would like to inform you that the proceedings of today will be uploaded on KFAS YouTube channel in the next couple of days. Also, a kind reminder on the survey that will show up in a few seconds for you to kindly fill out. Your feedback is important to us to improve on our future events. For now, stay safe, everyone, and have a good night.
Thank you.
Thank you. Thank you, Dana.
Thank you so much.
Thank you.